Hello! In this video, we present the third retrosynthesis of Brivaracetam, an antiepileptic drug. In this retrosynthesis, the key precursor is a chiral bicyclic compound formed by a cyclopropane ring fused to a butyrolactone, and its preparation is based on a homoalanine-type reaction. This precursor can be prepared from raw materials that are commercially available, as we will see later. The amide group functions as a retron, and a carbon-nitrogen disconnection opens the cycle, giving rise to an intermediate that contains two amino groups and a leaving group, which is represented by the letter X, where X could be a halogen. A functional group transformation of compound 2 generates the primary alcohol 3. The indicated amido group in 3 functions as a retron, and a carbon-nitrogen disconnection gives rise to intermediate 4, in which the substituent Y represents a leaving group, such as a halogen or an ethoxyl group, and to the derivative of the amino acid homoalanine, whose retrosynthesis was already presented in a previous video. The 1,5 relationship between the carbonyl and the hydroxyl group in 4 favors the formation of the chiral lactone 6. The propyl group in 6 can be considered to have formed as a result of the opening of the cyclopropane ring in 7 by a nucleophilic attack of organometallic reagent 8, which originates as raw material. This is based on a homoalanine-type reaction. Thus, a carbon-carbon disconnection generates the chiral bicyclic compound 7. In order to facilitate the opening of the cyclopropane ring through a nucleophilic attack, an ester group is introduced to the alpha position to the lactone's carbonyl group, in such a way that the alpha carbon is able to acquire a negative charge upon the opening of the cyclopropane ring, and in this manner, a carbon-carbon connection then leads to the production of lactone ester 9. Lactone 9 functions as a retron, and a carbon-oxygen disconnection opens the lactone, giving rise to diester alcohol 10. The cyclopropane ring 10 can be considered as being formed through the nucleophilic attack of the carbon atom that is bonded to the ester groups upon an epoxide group, and a carbon-carbon disconnection generates the epoxide diester 11. Subsequently, a carbon-oxygen bond disconnection then opens the epoxide ring of compound 11, thereby generating the chlorohydrin 12. The secondary alcohol in 12 can be generated by the opening of an epoxide group through the attack of the conjugate base of the malonic ester 13, which is utilized as a raw material. A functional group transformation applied to compound 14 results in the formation of chiral glycidol 15. The epoxide can be formed through an asymmetric sharpless epoxidation reaction to yield allylic alcohol 16 as a raw material. In summary, here are the main disconnections. In the following video, we will present the resulting synthesis.